I'm Lenora Clark, Director of Autonomous Driving and Safety Technology. Through a series of webinars, I will educate you on various materials used in the build of electronic hardware, the hardware that supports automotive safety systems. Throughout the series, we will look at designs from a perspective of printed circuit board manufacturing, assembly materials, and materials used to enhance semiconductor packages and IC substrates. I invite you to think of the parts of these builds and how they affect the whole. As we travel this webinar series together, I'll simply be your tour guide. I'll show you some cool things from a materials perspective, but ultimately you know your designs. You understand the challenges associated to them and the final expectations. You will choose the appropriate materials and deliver success in your product. But to help you along this way, to help you reach your goal of next level autonomy, I will supply valuable materials information and focus on 3 areas: form factor, performance, and reliability. Today, we will discuss the testing required for ADAS and explore a necessary material change to achieve enhanced reliability. The focus will be a high reliability solder alloy. As we create a supercomputer on wheels, we have to consider the significant influx of electronics in each system and what that means for overall vehicle reliability. So what exactly is meant by a supercomputer? Well, a basic definition states that it has great speed and memory, thousands of times faster than a personal computer. And this is directly relatable to a car's central computer. It must be able to make very quick, informed decisions. It will gather information on its surroundings, pull from a historical log of experiences, previous situations and programs to make an accurate, safe next move. Think about yourself. Think about how much information you're taking in when you're driving on a congested highway and you want to change lanes to get around a car that has abruptly stepped on its brakes in front of you. It seems like a basic concept to someone who's been driving for many years, but there's a lot of information to take in and react to all in a fraction of a second. Now we're going to turn this decision-making over to a machine that cannot wear or degrade. So in our previous installment, we discussed the effect of printed circuit board materials on 77 gigahertz radar designs. Staying close to that theme, today we'll look at the joining materials used for connecting the components to the printed circuit board. We will consider the necessary life expectancy of these systems and the challenges associated to radar, as well as all other advanced safety. Car makers are putting stringent test requirements on ADAS systems. You can see from the chart that the advanced safety systems require the highest number of thermal cycle exposures. But the greatest concern for an electronic system is thermal fatigue. Thermal fatigue is defined as the gradual deterioration and eventual cracking of a material, usually metal. It's a result of alternate heating and cooling. And if you think about it, you can imagine that the environment for any car electronic is pretty aggressive. Think of where these systems are. Next to the engine, baking out in the sun, they get really hot. But in addition to the location, the function becomes a thermal concern. We have a significant concern for advanced safety systems due to the amount of processing power that they require. These systems are getting hot just simply from running, simply from doing their own function. The image on the right is a thermal scan showing the hot silicon die at the center of a substrate package. So let's look at the impact that heat has on the electronics. We start off with the backbone of the design, the printed circuit board. It's a glass fiber weave, kind of like a sheet. Holes are then drilled and copper is plated to create the circuit, and then finally a surface finish is applied. There's about 180 other additional steps which we can't get into now. But after the PCB is finished, solder paste is applied. This is a paste material containing organics and small metal spheres, which then get heated, the organic is released, and it melts into an alloy. And finally, this joining material is taking semiconductor packages and IC substrate components and soldering them to the surface of the printed circuit board. This is the brains of the operation, right? The silicon chip gives life to the electronic, but the chip also has additional metals and plastics. So essentially, there's a lot of materials coming together to make all of this work. Organics, metals, metal alloys, and plastics. And when we bring these things together and heat them, they all heat at a different rate and they expand at a different rate. And we call this the coefficient of thermal expansion, or CTE mismatch, the fact that all of these things will move differently at different times. The predominant area of weakness is the solder joint interface. Thermomechanical forces put stress on the solder joint, and eventually that stress releases through a crack, and this crack can become an electrical failure. The best way to eliminate this failure would be to enhance the solder alloy. So again, if we look at this picture, you can see there's the packages on the surface of the board, they have certain materials. Solder paste is attaching them to the printed circuit board via a copper plated pad, and that's on top of your glass fiber resin substrate. Again, many materials that are going to expand and contract at different rates and likely in different directions. And now we're going to put more function into the packages. And the solder joint is actually getting smaller. Again, the point is, as we advance, packages are getting smaller, but they're processing more, so they're getting hotter. And this puts more pressure on the solder joint. We must stabilize or improve the materials. In this image, on this slide, I showed you that as we advanced in our radar systems, we moved from a quad flat pack to a ball grid array. And I wanted to point out the pad area of contact. On the quad flat pack, it's about 1,800 square millimeters. But on the BGA, it goes down to 490. So you can see that the contact area is significantly smaller. A crack could be much more detrimental. Again, the best way to combat solder joint pressure is an alloy enhancement. We alter the alloy movement to reduce fracture. And we do this through alloy development, such as solid solution strengthening, diffusion modifiers, grain refinement, and precipitate strengthening. The Inalot alloy was formulated for underhood automotive applications. A more rigid and reliable material was created through Inalot. And again, as I mentioned earlier, car makers are putting extremely stringent test requirements on ADAS systems, and it's not a surprise. From this chart, you can see that the originally chosen alloy, the SAC 305 or tin silver copper alloy, cannot withstand the thermal cycle requirements used for things like lane departure sensors and blind spot sensors. You have to use an enhanced alloy like the Inalot. And then as we progress to higher levels of autonomy, level 4, level 5, with traffic assist sensors and autonomous driving vehicles, it is likely that you will have to use an underfill or corner fill in conjunction with the Inalot alloy. Currently, our development labs have testing to analyze the results of these combined materials. And just one more look at solder joint reliability. It can be seen through shear strength. In our internal testing, the data shows that the quantity of thermal cycles has the greatest effect on shear strength, which is measured in kilograms, but that the use of the Inalot alloy drastically improves thermal resistance. As the technology continues to advance, each system will be required to have greater reliability, in many ways defined through thermal and mechanical stress resistance. Our Inalot alloy is the best available improvement for solder joint reliability on the market today. Ultimately, understanding how it performs with your designs will determine the resultant life. But it is a proven product which has been accepted by the automotive industry for over 15 years, previously for underhood applications, but more today for safety. To make advances in your technology, you will need advanced materials that match your expectations. We have over 60 years of electronics experience serving all market segments. We specialize in advanced materials, and we have a complete understanding of the expectations of the automotive market with a strong focus on harsh environments. In our next discussion, we'll look at how heat affects the performance of the semiconductor packaging and IC substrates. We'll discuss a specific material to extend the life of the package. I thank you so much for your attention, and I look forward to continuing the discussion.